All right, our last section of Unit 7 is going to be taking all of the proportions and similar figures and theorems that we used and applying them to indirect measurement, which is a method of using these formulas, similar figures / triangles, and or proportions to measure an object. All right. Okay, and the floodlights problem that you did in class is an example of using indirect measurement. You're going to see a few others down here in just a sec. On this example, you're told that Jenny is 5 feet 2 inches tall. To find the height of the light pole, she measured her shadow and the pole's shadow. So imagine sunlight being over here, and these are the two lengths of the shadows. She's 5'2", and we want to solve for x, the height of the light pole. Well, if they're standing in line together, a couple things are going to be true. They're both going to be perpendicular to the ground, the light and Jenny, both going to be forming 90 degrees, vertical to the horizontal ground. And then this angle down here is also going to be congruent because it's the same exact angle that's formed with the sun. It's the angle that's formed from the shadows to the ground, or the angle from the length of the shadow all the way up to the height of the light pole and to Jenny. It's going to be the exact same because they're standing in line. And now if you want to find the height of the light pole, we can just set up a proportion and cross multiply. The first thing we want to do is we probably want to write all of our units in the same, all of our measures in the same units. So you can see you have feet. Let's just convert these all into inches. So 15.5 feet in inches, just times 12, gets us 186. 5 feet times 12 is 60, plus 2, so Jenny is 62 inches. And then 7 feet times 12 is 84, plus 9 gets us 93. Okay, so now we have every single height in inches. Let's set up a proportion using the corresponding sides. So the length of a light pole is x. The length of, or the height of Jenny is 62 inches. Equals the length of the shadow cast from the light pole, so 186 inches. And the length of the shadow cast by Jenny, 93 inches. And then we're just going to cross multiply like we have been with proportions this whole unit. We get 93x equals 11,532. Divide this over. Maybe we'll get lucky and it goes in evenly. It does not. We get 124 inches. Sorry, it does go in evenly. But if we want this in feet, you can leave it as 124 inches. That's fine. You can also take your 124, divide by your 12, and we get 10 and a third. And then hopefully we know that a third of a foot is 4 inches, right? There's 12 inches. A third of 12 is 4. So 10 feet, 4 inches, if you wanted to do a quick conversion to feet for the height of the light pole. Let's try another example of indirect measurement when we're setting up proportions. Let's do this telephone pole here with this gentleman who's 5 feet 9 inches. Again, a quick conversion to get these all in the same unit. So this would be 60 plus 9, so 69 inches. 84 plus 8, 92 inches. 38 plus 4, 460 inches. And we're solving for the height. Okay, again, we know that these two triangles are similar because you have angle similarity. You have the angle that's formed with the ground, and if this is the length of the shadow down here, you know that the angle is formed with the ground from the shadow all the way up to the top of this person and of the light pole. It's going to be the same exact angle. You're standing in line. When we set up our proportion, it would be 69 to h, the height of this person to the height of the light pole, equals 92, the length of the person's shadow, over 460, the length of the telephone pole shadow, and we'll cross multiply again. Get 92h equals 31,740. Divide this over, we get our height equals 345 inches. Let's divide that by 12. We get 28 and 3/4. Well, 3/4 of 12 is going to be 9, so we get 28 feet 9 inches. All right. Okay, let's have you try the same or similar example using this person here who's 4 feet 2 inches tall, and we want to find the height of the flagpole. All right, first thing you probably want to do is convert these all into inches, so 240 inches, just multiplying by 12. 4 times 12 is 48, plus 2 is 50, so 50 inches. And 3 times 12 is 36, plus 4 is 40 inches. All right, go ahead and set up your proportion, solve for the height. We've got a height of 25 feet. If we did this correctly, your proportion should have been the height of the flagpole is going to be the same to the height of the person, is going to be the same ratio as the length of the shadow to the length of the shadow of the human. Cross multiply, divide by 40, and get 25 feet. Well, 300 inches. And then divided by 12 gets you 25 feet. All right. Next thing I'd like to talk about is you've probably seen proportions, or you've set up a proportion before using a scale drawing. So a scale drawing represents an object that's smaller or larger than its actual size. You see these all the time in maps. It's what's located on the bottom here. The drawing scale, it's the ratio of any length in the drawing to the corresponding actual length, right? So if we knew the length from Beijing to Shanghai was, I don't know, about that exact, no, it's say 800 kilometers. You could use that scale right down there and see, hey, this is telling me what looks like only 2 inches on the map is actually 800 kilometers in real life. Okay. Other examples. You've seen some on your homework. Here's a scale of just a kind of model toy doghouse here. And you're told that 1 inch actually equals 3 feet. If this model doghouse is 3/4 of an inch, well, then our proportion should just be 3/4 of an inch times 3. Just scale it up, multiply by 3. Gets us 9/4. 9/4 is 2 1/4 feet for the actual length of the doghouse. Let's do another example together. Let's do B here. In B, you're told that this scale, whatever this length is right here, which you kind of have to trust me that I printed this out and used a ruler and measured that little scale here as 1.2 centimeters. Okay, 1.2 centimeters is 300 meters. If we now want to find the length between Union Station and the library, that would be from here to here. You could take that scale with your hands and try to, you know what, I might be able to do it on here. Line these up. All right, I think you can move. Only problem is I might be changing the size of it, which might be difficult. But you would line those up and find out, hey, what's the actual length on this map from the Union Station to the library? I've done this in years past where I have it printed out, so just kind of trust me here that it's 4.8 centimeters. It's about 4 of those lengths. You can kind of see that here. 1, 2, 3, and 4, give or take. So 4.8 centimeters to our actual length equals the 1.2 centimeters of our scale to 300 meters in the actual length. And then we'll cross multiply. We get 1.2x equals 1,440 divide by 1.2, and we get x equals 1,200 meters. Actual distance from Union Station to the library. Okay, let's skip C for now, and I'll just let you try D on your own. D says, on a road map, Kristen measures the distance of 11 1/8 of an inch from Madison to Wausau. The scale on this map is 1 inch to 13 miles. What's the actual distance? It's a quick calculation there. Why don't you go ahead and use this scale to find the actual distance from Madison to Wausau. Go ahead. Okay, quick calculation here. I'm going to write this as an improper fraction, which is 89/8. Just multiply 11 1/8 inches by your scale factor of 1 inch for 13 miles. So just 13/1. And this gets us 144.625 miles. You could have written 144 5/8 of a mile, but that's perfect right there. Okay, using scales on maps, scaling up or down. Okay, the last thing I want to finish with is the similarity between perimeter and area ratios. Okay, and you're going to notice something here when we fill in this table down below. First, hopefully we can notice that this smaller rectangle is similar to this larger rectangle because all of the corresponding angles are 90 degrees. They're rectangles, so they have to all be congruent. And then let's check the ratio of the sides. 6 to 9 simplifies to 2 to 3. And 8 to 12 also simplifies to 2 to 3. Okay? So that's why these two rectangles are similar. All the corresponding sides are proportional and corresponding angles are congruent. Similarity ratio is 2 to 3. Let's complete the table and see what we notice about the ratio between the perimeters of the larger and smaller rectangle and area of the larger and smaller rectangles. Well, the perimeter for both 8 plus 6 plus 8 plus 6 is 28. Area would just be 8 times 6, so 48. Let's check the area and perimeter of the larger rectangle. 9 plus 12 plus 9 plus 12 gets us 42. And then for area, 9 times 12, 108. Okay, let's look at the ratio of the perimeters and the area. So for perimeter, it's 28 to 42. Let's simplify this down and see if we notice something. 7 divides into both of these. 7 divides into 28 4 times. It divides into 42 6 times. Oh, if we keep going, simplifying all the way down, the ratio of the perimeters, it's exactly the same as the ratio of the corresponding sides. Great. How about for area? 48 to 108. Let's reduce these both down. 12 goes into both. 12 goes into 48 4 times. It goes into 108 9 times. We can't reduce this any further, but maybe you notice something about the relationship between the similarity ratio and 4/9. It's just the similarity ratio squared. 2/3 squared gets you 4/9. So if you ever want to find the ratio, if you ever want to scale up the area, and you know the area of the smaller or the larger rectangle, you can just use that similarity ratio squared and find the area that's missing. Let's state those theorems down below here. If the similarity ratio of two similar figures is A to B, or 2 to 3rds, or 2/3 like we had up above, 2 to 3, then the ratio of the perimeters is also A to B, or 2 to 3 in the example above, and the ratio of their areas is A to B squared. And I just want to show you one example here that you can finish with. You know the perimeter and area of this larger rectangle. If we wanted to find the perimeter and area of the smaller rectangle, you just need to know the similarity ratio, right? So the similarity ratio here is 3 to 2, kind of similar like we had up above. Well, that means perimeter, it's also going to be a ratio of 3 to 2. So 72 over x would also equal 3 to 2. And we cross multiply, we get 3x equals 144. And 144 divided by 3 gets us 48. So 48 centimeters. Awesome. Let's do the same for area. Area would just be 315 to the area of our smaller rectangle. But now using this similarity ratio squared, so 9 to 4. Cross multiply, we get 9x equals 1,260. Divide by your n, divide by your 9. We get an area of 140 centimeters squared. Okay. So the ratio of the perimeters in similar polygons is the same as the similarity ratio of the sides. And for area, it's the ratio of the sides squared. Okay, you'll have a couple examples like that on the homework. We'll definitely go over those together in class. But use that floodlights problem as an example that we did together in class. And we will continue to practice these plenty on your test next week. Okay, good luck on the homework.